Hey everyone, and welcome back to this class, Deep Reinforcement Learning, Deep Learning in Python Part 7. In this lecture, we are going to implement a parameterized policy in Tensorflow for the continuous version of Mountain Car. If you don't want to code along, although I strongly recommend doing so, the relevant file for this lecture is pgtf_random.py in the subfolder Mountain Car. At the top, we have all our usual imports. Next, we have the hidden layer class, although I am not going to make use of it in this lecture. We are just going to use a linear model with RBF kernels. You are encouraged to try to turn that off and use a plain neural network if you want. Notice how in the hidden layer, I'm saving the parameters here, even though with TensorFlow, we don't usually need to do that. I want to have them so I can make a copy of this network later on. Next, we have the policy model class. This is going to be similar to before, but with some extra functions around copying. At the top, we copy all the arguments from the constructor. This is so we can make clones later. Next, we create the layers for the mean. Remember that the mean is unbounded, so the final layer activation function is identity. Next, we create the layers for the variance. Remember that the variance must be greater than 0. So the final layer activation is soft plus. Next, we collect all the params. Remember that we need to collect the params from both the layers for the mean and the layers for the variance. The next step is to declare inputs, advantages, and actions as before. The getOutput function is useful since getting the output for both the mean model and the variance model is the same. We add a little bit of smoothing to the variance to aid in exploration. Next, we create a random normal or Gaussian object. This has useful functions for sampling and calculating the log PDF, although we don't strictly need it right now. You'll notice I've commented out the optimizers, but they are still here. Technically, we don't need to do any fitting since we're doing hill climbing, but theoretically you could do both in some combination, so I leave that option up to you. Finally, we compile the predict op. Notice how we need to clip the value to be between -1 and 1. This is because the environment only allows actions between -1 and 1. Next, we define the set session function, which is just a simple setter. This is because it's easier to have all our models using the same session. Next, we have the init vars function. We need this because TensorFlow requires us to init vars before using them. We can't use the global variables initializer because if we call it at the very beginning, the later networks we create won't exist yet. But we can't keep calling global variables initializer either because then it would reset all the variables to something random and we would lose our best params. So we need to initialize variables only when a network is created, and only the variables that are part of the network. Next, we have the predict function and the sample action function. These are pretty simple. They just call things we already made. Next, we have some functions related to the hill climbing procedure. First, we have the copy function. This creates a new policy model with the same constructor arguments as it had originally. Notice how it also must set the session and init the variables of the newly created model. Then it calls the copy from function, which copies the parameters from one model to another. Next, we have the copy from function. Since we saved the parameters as an instance variable earlier, now all we need to do is loop through them. We use session.run to get the value, and then we use assign to set the value, but it's only a TensorFlow op, so we need to run it inside a session after. Next, we have the perturb params function. This is what will help us do the hill climbing. So what we do is, we loop through each param, and then with probability 0.1, we just assign a completely new random setting to the param. Otherwise, we take the current param and add some noise to it. Next, we have the play1 function. This one is pretty simple. Next, we have the play multiple episodes function. This just plays a bunch of episodes and returns the average reward. Remember that we want to play multiple episodes to test each parameter setting to reduce the variance. We also want to test how well our model can do over 100 iterations, since that is how you're judged on OpenAI Gym. We also have the print iters argument that will print the average after each episode, so that you don't have to wait for all 100 episodes to see the result. Next, we have the random search function. This is very similar to the random search we saw earlier. First, we initialize total rewards to be an empty list, where we'll be collecting the rewards for each parameter setting. Then we initialize best average total reward, which helps us keep track of the best parameters we've seen so far. Next, we have best P model, which will be the actual model containing the best parameters. Then we have the number of episodes to test each parameter. I found 3 to be sufficient. Next, we do a loop 100 times. I found this to be sufficient for finding a good setting of hyperparameters. In the loop, we make a copy of the best model, we call it temp model. Then we perturb its params. Then we play a few episodes with these settings and obtain the average reward. We append this to our list of total rewards. If this average total reward is better than the best we've seen so far, then we set the best model to be this new model. Then we exit, returning both the total rewards list and the best model we found. Next, we have the main function. This is mostly what you expect. We create the environment, feature transformer, and the model. We create a session, set the session, and init the vars in the model. We have our code block for monitoring. Then we do a random search. We print the max total reward. Then of course we want to check these parameters for consistency, so we play 100 episodes and print the result of that. Finally, we plot the total rewards as a function of time. Notice how we are not plotting a cost to go function. This is because this method doesn't require a value function at all, although technically, now that you have a policy, you can use policy evaluation to calculate it. I leave this as an exercise for you if you're interested. Let's run this and see what we get.